Good morning. Today in lab, we're back in Physics 4B lab here. Today in lab what we want to do is a measurement of absolute zero, so I hope everybody wore their really warm clothes today. We're going to find out what the value is for absolute zero. Now when you're thinking about absolute zero, you're going to say, whoa, absolute zero's temperature is 0 Kelvin. But what does that really mean? How did researchers initially determine the temperature of absolute zero? So we're not going to use the Kelvin scale. We're going to imagine we don't know anything about the Kelvin scale. We're going to work in terms of Celsius. So, researchers in determining what's the value of absolute zero had to work with some sort of an existing scale, and then they knew that absolute zero would be way negative on that scale, right? They knew from refrigeration experiments that they could go to much colder temperature. Well, the question became, at what Celsius temperature does all molecular motion stop? Okay, just what temperature do you have to lower things to? Now, something that was suggesting the existence of absolute zero was the ideal gas model. So we're going to be using that today. We're going to be using the ideal gas formula, starting from that and indicating what absolute zero would mean. So in class, in lecture, what we've been talking about is that temperature is a measure, it's a gauge of how much kinetic energy individual atoms and molecules have in a substance. So the idea is, well, if we take away the kinetic energy, if the molecules stop vibrating, they stop rotating, and they slow down their translational motion to where they're basically not moving at all, if we remove all of the kinetic energy, that must be what absolute zero is. That's what we want to define as zero on some sort of an absolute scale like Kelvins. So we got to find out what that value is. What is the value of absolute zero in Celsius so that we can make that adjustment and define the Kelvin scale. So here's the formula. Our objective is to get that absolute zero measurement. Here is the formula now. Instead of PV equals nRT, I've put in T minus T naught, where T naught is absolute zero. So what that does is that creates an absolute temperature measurement here. How far above absolute zero are we? Now, what this formula suggests is that if we maintain a constant volume and we maintain a constant number of molecules or a constant number of moles, if we have a fixed sample of gas molecules, then the pressure should be directly proportional to this temperature. That would suggest a graph like this. So let's say that we take some collection of gas molecules. Now, what we're going to use for that is this clever device right here. What this is it's a, we've got this volume down here. We've got this steel spherical container with this long measuring tube. But we've got this sample of gas molecules that are inside here. And what we're going to be able to do is we can open this up. We've got, it's kind of like a bicycle valve tube here, or a car valve. What we can do is we can open this up and let some air molecules in or let them out until the pressures equilibrate. So we have a pressure gauge built into this. Now, atmospheric pressure, which I'm guessing the room right now is pretty close to atmospheric pressure, would be about 100,000 pascals. Now the big numbers here are pounds per square inch. It's actually the blue smaller numbers here that are measuring pressure in kilopascals. And this is measuring pressure absolute. You know, you're used to picking up maybe a typical pressure gauge would read zero, right? You pick up a pressure gauge and you look at it and you go, well, it reads zero. Is there zero pressure? What most gauges are designed to do is measure pressure compared with atmospheric pressure, compared with the surrounding pressure. But these devices are designed to measure the absolute pressure. they're comparing atmospheric pressure with if there was no pressure at all in the atmosphere. So this is giving us a reading. It's giving us a non-zero reading. And it's actually saying that, yeah, it's pretty close to 100, just past 100. So it looks like 102,000 pascals, 102 kilopascals, 103. Well, that is what atmospheric pressure is. So that's kind of what we would expect, starting out with this gas sample. Now, this is going to give us a constant volume and a constant number. So when we run the experiment, what we do is we change the temperature. Now, when we get to the close-up videos here, I've got over here on the tables, and I've got some water heating up. That's going to provide a hot temperature environment for our air molecules. And then I also have an ice bath getting ready. I got some ice actually brought in from home. I've been collecting ice. And I'm going to make an ice bath. So what we want to do is we want to have temperatures of somewhere around 0 Celsius and somewhere around 100 Celsius. And what that's going to provide for us on our scale here is, look, if I take a collection of gas molecules starting off at 0 Celsius, that would be in my ice bath. And then I take those gas molecules and from the ice bath, and I move them over into the high temperature region. If I do that, the temperature is going to go up, pressure is going to go up. I'm going to have more kinetic energy in those molecules. So what I'm keeping track of, or what we're keeping track of in this experiment, is, when I transfer from 0 Celsius to 100 Celsius, how much does the pressure go up? Because according to the ideal gas model, what should happen is once I measure how we go from point A to point B on this is a pressure temperature graph, once I've identified this slope, I can extrapolate this line to lower and lower temperatures. And wherever the pressure goes right to 0, wherever it crosses this temperature line, that should be absolute 0. Right? That should be absolute 0 is where this extrapolates back. Now, the ideal gas molecule is based on gas molecules that behave ideally, but in reality, gas molecules have a little bit of stickiness to them. They take up a little bit of space. So, it's a little tricky here because we're trying to define what we mean by a temperature scale. And to do that, we're using a sample of molecules that are not quite ideal. We're making adjustments for that. And then using this ideal particle model, this ideal gas model, to figure out where absolute 0 would be. Okay. So again, we're using this constant V, constant N. It gives us a graph that looks something like this. Now, if I take a look at this graph, the vertical axis is pressure. We're going to be measuring those in kilopascals. The horizontal axis is temperature. We're going to be measuring that in Celsius. If you take a look at this graph with these lines extrapolated backwards, what we've got are a couple of right triangles on our graph. So what we have for the sides of this triangle, from point, I guess down here, right? From here out to here is, that's temperature A minus temperature naught, which I'm calling absolute 0. And then similarly, at the higher temperature, that distance then would become TB minus T0. In the vertical directions, we have pressure A and pressure B. Well, if these are similar triangles, then we can, now I've written down the resultant right here. We can actually show that if I take all of this information here and set this up as some ratios, we can solve for T0. T0, or absolute 0, is going to be TA PB minus TB PA over PB minus PA. Now that works for the triangle that we have set up here. Notice what we're going to do is we're going to come back and we're going to run this at some lower pressures. So point A is going to be at 1 atmosphere pressure, and point C will be at 1 atmosphere. I didn't quite get those lined up. I was trying to make this more visible. Point B is going to be above atmospheric pressure, and point D is going to be below. So when we transfer the gas molecules from the, let me get this in red. When we transfer the gas molecules from the ice bath to the boiling water, that's the transformation that we're going to see. Now during that process, I can't open up the container. I have to keep all those gas molecules in there, right? Because when we're doing this measurement, we're going to be at constant N. Now once I get measurements made at both point A and point B, then I can keep this in the hot water and I can release the gas molecules. It's going to be at higher pressure than atmospheric. If I open it up, I'm going to be able to release it back down to 1 atmosphere. So C is going to be at 1 atmosphere. And A is going to be at 1 atmosphere. Now I'll close things back up, and then we'll do another measurement, taking the gas molecules from the boiling water back to the ice bath. So let me write this. Here is the ice bath. Now that's going to be very close to 0 Celsius. So we're just going to go ahead. I've got some thermometers. We'll use the thermometers to verify the temperatures, but we probably should just report that as 0 Celsius for the ice bath. And then over here, we're going to have the high temperature water, basically the boiling water. So we're going to say that this is probably going to be at 0 Celsius. Now this is going to be around 100. We'll have to get the thermometers out and check and see if these match. In any case, I did the derivation is here. So here I did the ratio of temperatures to pressures, and I did a bunch of lines of algebra. You guys should be able to find your way through that. So that's something you should be able to follow through. And the results I got were these two formulas. So this is the data from points A and points B. And this is the data for point C and point D. So now that we've got those formulas, what we want to do is, well, we want to set up some data tables. So in my data table, I'm going to need pressures and temperatures at point A, pressures and temperatures at point B, and then I'm going to need another data table that has pressures and temperatures at point C and point D. So this is just showing going from point A to point B. Now, as we've seen in our previous lab, what we want to do is we want to do some multiple number of runs. If we just do this once, we're thinking that one measurement probably isn't as reliable if we go back and do this a few times. So the plan would probably be to go through and do this, let's say 3 times. So I'm going to put in 3 as the number of trials that we're going to do here, and then we'll fill in that table. Similarly, we're going to go from C to D 3 times. So 3 times from A to B, 3 times from C to D. That should give us like 6 values of absolute 0. And once we get all those absolute 0 values figured out, we can average them, right? So that's kind of our standard procedure with a lot of these measurements that we do in lab. We want to do several runs. If we do it once, we're really not sure how reproducible the results are. If we do it twice, we start to get an idea. By the time we've done it 3 times, we are really starting to get kind of a feel. If you've taken some statistics classes, you know, doing a measurement once really doesn't tell you much about the uncertainties in your numbers. Doing it twice gives you some information. 3 really gives you a boost. And then you can continue. You can continue to take more and more data. You kind of run into diminishing returns. 2 and 3 are where you get a big boost in determining kind of how much uncertainty you're going to have. So a lot of times we'll do, you know, 3 runs is a charm, is kind of the approach here. All right, once we've got all of that determined, so here's our data tables. Well, we also need the results table, right? So the results table, now we've got a couple of options here. in the results table, if you want to, you can just report one overall value. Now, I think what I would prefer, I guess, we've just been doing this a few weeks. Why don't you plan, let's plan on this. Let's plan on reporting all the individual runs and then an overall average. So we could report, 1, 2, 3, 4, 5, 6. And you guys can be a little creative with your results tables too. But the items that you do want to make sure that are included here are, you want to have values of the measured values that we've made. And then compare that with the accepted value. Now the accepted value for absolute zero is minus 273.15 degrees Celsius. So that's the number that you can compare with. Now, the percent difference formula, we talked about that in last week's lab. Let me go ahead and, I've kind of boxed myself in here. But percent difference, and let me see if we can just slip it in right here. I'll get rid of this. Make a little space right there. So our formula for percent difference is going to be measured minus accepted over accepted times 100%. Now 100% is the same thing as 1. It's just kind of doing a units conversion from a fractional difference into a percent difference. So we're going to use a relative percent difference here, and then we're going to report that. So, the percent difference is, I don't know, let's say that the number you come up with is 3.4, so that's an example. You run the formula and you find out that the results you have are 3.4% higher than the accepted value. So if you've got any questions on this, stop by, office hours, lab hours, and let's get that figured out. Because this is going to be really important for us. Those percent differences are such a handy reference. Now another thing we talked about, I think some last week, but let me emphasize this again, is that when we come in to do lab, we're not trying to reproduce any particular numbers. That's not the way science works. So I'm always a little concerned that a lot of times when students come in, they've got kind of a career of high school lab courses and whatever, and a lot of times they've been systematically rewarded for getting the number that the teacher wanted you to get. Okay, and that's actually not how science works. The way science works is you kind of put out of your mind other measurements that other people have done. What you want to do is you want to come up with a measurement that's completely unbiased. So we're not trying to get a particular number. And let me, this is kind of a warning for your lab reports too. If you say in the lab report, this one run was really good because it came very close to the accepted value, no, that's not the way science works. Again, we're not trying to get any particular value. So what we would say is any run where you guys have been very careful and been very careful about all the readings, very careful about all of the steps in the procedure, those are all equally good runs. It's not based on how close you get to some number that somebody wanted you to get in a result. We would never find, we wouldn't discover new things in science if people were always just trying to get the results that somebody else has already gotten. Okay, anyway, that's my recommendation or advice for the day. So again, we want to be as careful as possible on all the measurements, and then whatever we get on those measurements, we want to present that as accurately as we possibly can. We're not trying to get any particular value. Okay, so watch for that in your lab reports. Don't say the numbers are good based on whether or not they're what we wanted to get. Okay, it doesn't work that way. All right, questions on any of this? I feel like we've kind of gone over the stuff on the board. What I want to do now is I want to switch over and take a look at the setup. All right, so we needed the high temperature environment. I've got a bunch of water that has come to a full boil over here. I was just checking the temperature on our thermometers. I like using two thermometers. Two thermometers means that we can kind of double check, see if there's consistency. One of the thermometers is reading just above 100, like 100.3 or 100.4. One of them was reading just below. Let me check it one more time here. And so I am looking to see. Now there's always a concern with the thermometer sitting on the bottom that we're reading too high of a temperature. But it looks like, yeah, one's just a little bit above 100, almost at 101. The other one is just below, like 99.9 or something. Anyway, I'm going to pull those thermometers out. I'm probably going to go with 100 Celsius. We'll see what I decide. I may end up just figuring that the thermometers have little built-in, they've got their own limitations, and that we're probably pretty close to 100. Then for the ice bath, what I've done is I've brought in some ice from home, collecting ice. So I'm going to put that into this other container. Get an ice bath set up here. And so we can work back and forth between those temperatures. So we want to be able to go from the high temperature to low temperature. Maybe I'll try one more bag like this. For part of it. All right, so I'll put this back in here. Keep the ice for some other labs. So here's the ice bath. Let me get some water that we can dump into that, or maybe just go fill it with a little bit of water in the bottom. Want to get good thermal conduction here. So this has actually worked almost too well. I was a little concerned that the ice would be melted, but instead, the ice is not melting much, but we want to get a nice, cool bath for it. So I think what we had talked about with the procedures was the first step was to take our sample of air, put it down in the ice bath. I'm going to put it down inside there. And then I'm going to take the valve and open this up. So I can see that there's a pressure drop taking place already. But what I want to do is I want to get this at atmospheric pressure. That was what the plan was. So I'm going to keep letting air back in while we do this. And then I want to get some thermometers in here also. So again, maybe put a couple thermometers inside here and see what temperature we're at. It's ice water. So I'm thinking that we're going to get something very close to 0. Let's see if that's actually what we end up with here. So I'm going to turn this water down. I guess we've got a really vigorous boil going here. I want to make sure that it continues to boil though. So I'm going to keep that temperature there. And then okay, so the temperature I'm seeing in the ice bath looks like it's leveling off right at 0.1 on one of my thermometers. The other thermometer right at 0. So 0 sounds pretty good. I got good thermal contact here. Now, one of the limitations of our lab today is that we're assuming that the entire set of molecules of air inside are at 0 Celsius. Now that might not be true because we've got this small amount of air that's up in this higher region where the pressure gauge is. But it does seem like it's reading right at 0, so I'm going to get that written down. This one just a little bit below 0 now. So, and then one last time, I'm going to let the air molecules equilibrate. And each time I've done this, the pressure is like at 102 kilopascals. All right, so now, here we go. We're going to take this air sample. Now the number of molecules is fixed at this point. So I'm going to transfer this over into the high temperature water. I planned ahead here, I hope. I left some space so that this would fit down inside. And then the pressure that this has gone to is 100 and looks like 130, 140. We are at 140. I'm going to say right at 140 or 139 kilopascals. I think it's a better measurement for this. Okay. So I think we took a look at the scales before with this, but kind of see where the readings are. So again, let me put this back inside. Now I'm going to have to get all this stuff written down, but I've got a record, a video record, an audio record of all this. So I'm going to say this is at 139 kilopascals. Maybe I will get that written down right now. So I'm going to write this down. 100. I went from 102 kilopascals up to what I'm seeing is 139 kilopascals. Temperatures, I'm going to say, is from 0.0 Celsius to 100 Celsius. It does look like the thermometers are saying that we're really within a few tenths of a Celsius of those numbers. Okay, I want to reverse this just so we see what the reverse process looks like. So I guess what we had talked about doing here is, I want to make sure that we maintain the boil. What we had talked about doing here was going to the higher temperature and then coming back down to, it looks like 102. So it did come back down to the same atmospheric pressure. And now I'm going to keep that constant. So I'm going to keep the number of molecules in here constant and transfer it back. Put it back over into our ice bath. Whoa, we got to get it down inside. So we're getting all the way down inside of our ice bath. Make sure that this is fully covered with the ice, and it's sitting down in the ice water. And let me take a couple of readings here too. The reading that I'm getting here is just a little bit above 0. So about 0.3, 0.4. This other one is reading just below 0. So our thermometers do have limitations to them. And just setting a whole series of our thermometers next to each other, you can see up to a Celsius and a half difference between them. So with different experiments that we're looking at, we have to take that into account. Always remember that it's kind of plus or minus 1 Celsius in our thermometer uncertainties. Now let me just check here too. I did want to go back and check and make sure. And this doesn't look like it's boiling as vigorously as it was. I hope we were at a good temperature when we took that last reading. This thermometer right now is saying that our water, and it's taking a little while to come up here, but it's kind of shooting up. Let's see what this gives us for a temperature reading of our water. Now, what's going to happen is we're going to do this 3 times. So I'm going to go through this and cycle back and forth 3 times. keeping track of the pressure. Oh, and I never got this last pressure reading. I've got to make sure that we get to this. So this last pressure reading, this is quite a bit lower now. The pressure went down to, that is 50, 60, 70, 80, 76. I'm going to say, that's probably kind of at the limit as to what we can do. I'm going to say 76 kilopascals. So what we've got here is starting at 102 kilopascals and then dropping down to 76 kilopascals. Now the temperatures, I'm thinking the temperatures still seem to be pretty good using, in this case, a starting temperature of 100 Celsius and then going back. Let's see if, yeah, with the hot water going back, we're getting the temperature right back up there at 100. Okay. So I think we're good. I think I'm going to turn this down. Well, actually, I need to leave it on because I need to get the rest of those measurements. So I'm going to turn this down a bit. I do want to keep the boil continuing and keep an eye on the thermometers here. But that's it. So we've seen the pressure increases, and then we've seen the pressure drops. At the pressures and temperatures we're working with, air behaves very, very much in agreement with the ideal gas model. So we should be able to come up with some numbers for absolute zero from these. So I'll plug those into the formula and see what we've got. One of the things I do want to mention before we wrap this up is that for the lab reports, make sure that you include, well, of course, the results table, the data tables. Also, I want to see the graphs. So please include graphs plotting the data and showing, what the plots look like, and then extrapolating those plots back to where the lines cross the, horizontal axis, where they're crossing the temperature axis. All right, any questions with any of this? Stop by office hours, stop by lab hours, and we'll get those questions taken care of. All right, we'll wrap it up here.